Hello everyone. So we are Caleb Mugisha and Kudus Mangistu. And on this video we are going to explain about what an image convolution is and the application of linear algebra on image convolution. So at the end of this video, we hope you understand what are image convolutions, what do they do, why to use them, and how to apply them. Okay, so first to start, we can think of an image as multi-dimensional matrix containing pixels. So if we can represent an image using a matrix, we can manipulate this matrix by applying various matrix operations such as matrix multiplication and transformation. So if we go down and if we see this figure can be represented by this matrix, this 0 and 1 matrix. So this image is represented by this matrix where 0 means the box contains nothing, which would normally appear as transparent or white, and 1 indicates the box is filled, and in this case filled with black. So basically, like if you ever used an image editor or softwares to sharpen, blur, to make it smaller or larger, that is what an image convolution is. So next, let's go to the technical terms on image convolution. So first, let's see what kernel is. So kernel is a square matrix which we use to convolve an image, which means to blur or sharpen whatever we want. So a kernel is a square matrix which we use to convolve an image. So the next one is origin. So the origin is the position of the kernel, which is conceptually above the current output pixel. And what's pixel? Pixel is the very small parts of an image, the smallest parts of an image. And as I said before, an image convolution is the process of adding each element of an image to its local neighbors written by the kernel. Okay. The next one is filtering. So filtering involves the application of matrices that perform useful functions such as noise removal and image enhancement. And the last one is color values. So color values describes the degree of lightness and darkness of a color. Okay, so now let's see why we convolve images. So the first reason is to smoothen the image, and the second one is to sharpen, the third one is to intensify, and the fourth one is to enhance the image. So we convolve images for these reasons. So next, Kali will explain about the application of linear algebra in image convolution.
Thank you. So I will be explaining the application of linear algebra in image convolution. So as my colleague said, an image is represented by a matrix having pixel values of the images. Pixel values being represented by color values of red, green, and blue. So the idea of image conversion, for understanding it, you have to understand what a kernel is. A kernel in this figure is represented by this red block or matrix, 3 by 3 matrix. So the idea of conversion is to decide on an XY coordinate of the original image say here in this figure, we decided this, if you can see beneath the red block, it's transparent, 202. So the idea is to find an xy coordinate and then put the middle coordinate of the kernel to that element. And then doing conversion is just taking the elements above and the numbers above and beneath, the matrices above and beneath, and multiplying them, and then taking their whole sum, and then write that sum in the in the output matrix to the point where you the center, like the xy coordinate you decided. You have to this sum -1 times 93 plus 0 times 109. You add them, you multiply them, all this number consequently, and then their sum, write it in the output image to this position in the output image, because the output image, the matrix, the input matrix comes the same as the dimensions are the same as the output image. So this is what I was talking about. And then you repeat this process all along all the points of the input image, input matrix. So this is the formula of what I was talking about. And so we try to make a simulation of image conversion with Python, using Python, uh, 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 NumPy library, and OpenCV. So this is a simulation try to do, if you can see my screen. So running this code, we used a picture named Kidus, PNG format, and then we convolve it, but here we trying to blur it. So if you can see, when I run this code, this is the original image, the kidus.png image. This is the convolved image. It's convolved by a smaller kernel, but if you want to increase the intensity of the blurring, we can increase the kernel. So this is what is done by in this matrix, in this, no, sorry, in this blurring. You can see this is more blurred than the previous blur. Okay, so following on, this is the code. We try to make it simpler by only focusing on blurring. So what are the real life demonstration or application of image conversion? They include blurring, sharpening, edge detection, and noise reduction. Blurring is what I just did, and then uh, sharpening is making an image more I don't know the word, but sharp, more alive, I would say. And then noise reduction is just removing some unwanted elements in the image. And then edge detection is just detecting the edges. So the relevance and importance, as you can see, this can be used in, as my colleague said, in photo editors, where we need to blur image, we need to sharpen it, we need to change the edges, we need to remove some elements in the image or sharpen it. So in contrast, though image conversion is awesome, as we try to go through, it has two dangerous flaws, which include translational invariance and pooling layers. I will not be talking about translational invariance because it's out of my scope, but I'll be talking about pooling layers. Pooling layers involve is take an example of a face. Say I want to do a conversion of my face. Say when I do the conversion, pulling layers in means like this is the position of my nose, and after the conversion, my nose comes, say, at this position. This is not my image. A lot of information is lost, and you know, maybe impossible to retrieve after the conversion, after the image is convolved and saved, which is a big flaw. So summarizing what we said, we can filter and modify images by interacting with their pixels, as images are represented by matrices of their pixels, and then that interaction occurs with conversions, and Conversion use canals as described in the presentation. And then a canal is that red block I described as my colleague said, and then it represents the area of each operations and weighs values and the anchor point. Thank you. This was all.